I'm going to use this video to explain the inclined plane to you. It's very simple. So this is the inclined plane, just like a right angle triangle. So something like this. This is the inclined plane. So it has an angle theta here. This is the effort. This is a drum, a piece of drum that someone is pushing like this. So when the person pushes this drum, at the end of the day, the drum will get to the top here. So now look like this. So the person applied an effort here. This is ordinary, like normal ground here. This is normal ground. So you notice something like this drum has moved this distance, which is x. Maybe it has covered this distance x. The drum has covered distance x, while this load here, which is L, it has gone like vertical distance. It was on the ground before, like normal ground, but now it is now high above the ground. It has covered distance h or height h. So the efforts move through distance x. Okay, so the efforts move through distance x, while the load moved through this height h from here, this lower ground, it came here. That's height h. So what's the velocity ratio? Distance moved by effort over distance moved by load. Distance moved by effort is x, so that will be x over distance moved by load is h, x over h. This is the velocity ratio of an inclined plane. So you're just doing the hypotenuse divided by the opposite. But if you check this thing very well, if you do sine theta for this right angle triangle, we do sine theta is so that will be opposite over hypotenuse. Opposite is h divided by hypotenuse is x. That's h over x. If you check these two, they are reciprocals. This one is x over h. This one is h over x. That means they are inverse of each other. So you can say the velocity ratio of an inclined plane is equals to 1 over sine theta. This is the formula for the VR of an inclined plane. So keep that in mind. So that's what they are trying to prove at this point here. So the velocity ratio of an inclined plane is 1 over sine theta. So now this inclined plane, this object will move from this distance to go up like this until it gets to this particular point. So this is the efforts that they are using to pull this load up. They are applying these efforts to pull it up. Okay. Now the next thing to note is, what if there is friction? If there is friction, this object is going up. They are pulling it up like this. If you are pulling it up like this, that means friction will be acting backwards like this. Friction opposes motion. So because this object is on an inclined plane, the weight will not act vertically straight like this. It is if the object is on a flat ground like this, that's when the weight will act downwards. But because the weight is bent, as in the surface is bent like this, so the weight will bend like this. So it will have another component that will be acting like this. The weight will act parallel to the inclined plane. So the component of that weight is mg sine theta. So the component of weight that is parallel to this plane is mg sine theta, while the one that is at 90 degrees to it is mg cos theta. I know that weight and normal reactions are the same. So the normal reaction, which is the vertical force here, will be mg cos theta. Normally, it's supposed to be the same like this if it's on normal ground. Two of them, this will be r, normal reaction is an upward force. Then mg, which is the weight, is a downward force. Two of them are supposed to be equal like this if it's on a flat surface. But this thing is not a flat surface, it's an inclined surface. So that is why the mg, which is the weight, you have to look for its component that is parallel to the plane, which is mg sine theta. Then the one that is at 90 degrees to it, which is mg cos theta. So this weight is acting perpendicular to the plane, mg cos theta. Then it will be equals to the normal reaction, which is r. So the efforts now, what will be the effort if there is friction? If there is friction, this stuff here will be acting backwards like this. You understand? To be acting backwards. So these two forces will be acting backward, mg sine theta and mu r. Mu is the coefficient of friction. So the effort will now be in this direction, E. The effort is pushing it up. So that means the effort is going against friction and mg sine theta. So backward force is always equals to forward force. That is why the effort here is equals to mg sine theta plus mu r. Mu r is a frictional force there. That's why they got that one. Then you can use R equals mg cos theta. Don't forget that R equals to mu mg. So if you want to add more efficiency to it, you can just write big R is mg cos theta. You can see it from here. This is mg cos theta. Downward force, we go to this one here. So R is equals to mg cos theta. That one is a formula on its own. R is equals to mg cos theta. You understand? Then the next one. So technically, the reason why it's like this is because the effort is going up. Or they are pushing this thing up like this. Because they are pulling it up. Because they are pulling it up, it will go against friction. Okay, but in this case here, they are assuming that the object is coming down. But if the object is being pulled up like this friction that is here, will be acting backwards like this. So that means these two forces, mg sin theta and frictional force, are acting against the forward force, which is the effort. So that's why the effort must be equal to the sum of the two of them. You understand? That's if there is friction. Then this mu here is the coefficient of static friction between the object and the plane. So when there is friction, you always use mu. This mu is called the coefficient of static friction. Now, what would be the mechanical advantage? Mechanical advantage is always load over effort, Abi. Like you know, it's load divided by the effort. So what's the load? The load is mg. That's the object itself, mg, divided by the effort. What's your effort? Your effort is the combination of these two guys. That is why this is load divided by effort. Then from there, you can see that mg is common. If you factorize mg out, you can cancel mg out. You're going to get 1 over sin theta over mu cos theta. You get, this is only if there is friction. No? Assuming there is no friction, it will not be like this. This mu cos theta part will not be there. That's if there's only friction. If there's friction, mechanical advantage is 1 over sin theta plus mu cos theta. Then what will be the efficiency? Efficiency normally, as we all know, is MA over VR. You understand? So MA over VR will give you sin theta over sin theta plus mu cos theta times 100%. Don't forget that your MA is 1 over sin theta like this plus mu cos theta. But you are doing 1 over VR. Like if you look at this MA over VR, it is like saying you can write MA. You can write MA over VR. You can write it as 1 over VR times MA. Two of them are the same thing. So if you're writing 1 over VR, you can write sin theta. Then don't forget that VR is equals to 1 over sin theta. VR is 1 over sin theta. So that means 1 over VR will be sin theta. So if you just manipulate that, you will get the same formula that is here. But this formula, I don't need to cram it. Just know that it only comes into effect when there is friction. There's no friction, the formula will remain the same. M over VR times 100%. That will be the efficiency. So that's all you need to know about inclined plane. I hope you understand.